Should the near-Earth asteroid Bennu impact Earth in the future, it has the potential to inflict significant global harm despite being much smaller than the asteroid responsible for the extinction of the dinosaurs as indicated by recent research. Astronomers project that Bennu has a probability of 1 in 2,700 of impacting Earth in September of 2182, corresponding to a likelihood of 0.037%. The asteroid, identified as containing the essential components of life based on recent analysis of samples brought back to Earth by NASA OSIRIS-REx mission, is classified as a medium-sized celestial body with a diameter of approximately 1,640 square feet, which is 500 meters. In contrast, the asteroid that impacted Earth 66 million years ago, resulting in the extinction of the dinosaurs, was estimated to have a diameter of around 6.2 miles, 10 kilometers, and is recognized as the most significant asteroid to collide with our planet. A research team has examined the potential consequences of a future impact from Bennu, despite the small likelihood of such an event occurring. Their modeling focuses on the effect of a collision with Earth encompassing its global climate and ecosystems both on land and in the oceans. Findings of this study were published on Wednesday in the Journal of Science Advances. Medium-sized asteroids such as Bennu are estimated to collide with Earth approximately every 100,000 to 200,000 years as indicated by the research findings. The study revealed that such an impact could trigger a global winter, resulting in decreased rainfall and a cooling of the planet, among other long-lasting effects. It is also suggested that early humans may have endured similar conditions during past asteroid impacts. Our early human ancestors might have encountered some of these medium-sized asteroid strike events, which could have influenced human evolution and potentially our genetic composition, stated Dr. Lon Dai, the lead author of the study and a postdoctoral research fellow at the IBS Center for Climate Physics at Pusan National University in South Korea. The researchers employed climate models alongside the capabilities of the ALDEF supercomputer at ICCP to simulate various scenarios involving a Bennu-type collision with Earth, primarily examine the consequences of injecting between 100 million and 400 million tons of material into the atmosphere. The findings indicated that significant disturbances in the planet's atmospheric chemistry and climate within 3 to 4 years following the asteroid's impact. Initially, the collision would result in the formation of a substantial crater and propel debris into the atmosphere surrounding the impact zone. According to Dai, the event would also produce a powerful shockwave and induce seismic activity. The substantial release of aerosol and gases from the impact could rise into the atmosphere, leading to long-lasting alterations to Earth's climate. Should Bennu collide with the ocean, it would instigate enormous tsunamis and release vast quantities of water vapor into the atmosphere. Such occurrences could result in a prolonged depletion of the ozone in the upper atmosphere, persisting for several years. The climate-active erosives, such as dust, soot, and sulfur, may play a role in inducing a prolonged cooling effect following the impact, according to Dai in an email. He noted that while aerosol-induced cooling could occur, greenhouse gases, particularly carbon dioxide emissions, are likely to result in long-term warming. In the most severe scenario, where 400 million tons of dust are suspended into the Earth's atmosphere, a global impact winter would ensue, characterized by colder temperatures, diminished sunlight, and lower precipitation levels as stated by Dai. Dust particles elevated into the atmosphere would capture and diffuse sunlight, hindering its penetration to the Earth's surface. This reduction in sunlight would lead to a swift decline in global temperatures, potentially decreasing as much as 7.2 degrees Fahrenheit and 4 degrees Celsius. Furthermore, as global temperatures fell, precipitation could diminish by approximately 15% due to a decrease in evaporation occurring at a ground level, as indicated by the study's findings. Additionally, the ozone layer might experience a depletion of up to 32% according to the research. The authors of the study also point out that the intensity of these effects could vary significantly depending on the location of the strike. The findings indicate that dust particles with an atmospheric lifespan of up to 2 years may trigger a global impact winter lasting over 4 years post-impact, according to Dai. This sudden impact winter would create adverse climate conditions detrimental to plant growth, resulting in an initial decline of 20 to 30% in photosynthesis across terrestrial and marine ecosystems. Consequently, this could lead to significant disruptions in global food security. Modern humans have not experienced an asteroid impact. However, Dai drew parallels between the environmental consequences of such an event and other significant sun-blocking catastrophes, including major volcanic eruptions. The projected global cooling outlined in the study is similar to the climate disruptions caused by the supereruption of Mount Toba in Sumatra, which is regarded as one of the most significant eruptions in Earth's history and likely altered the global climate approximately 74,000 years ago. According to Nanja Draban, an assistant professor of Earth and Planetary Sciences at Harvard University, the findings of this research are consistent with the effects observed from previous impacts throughout Earth's history. Draban stated that numerous historical impacts were significantly greater, resulting in effects that were frequently more intense and enduring. He noted this study is particularly noteworthy as it demonstrates that even impacts considered relatively minor could release sufficient dust to drastically hinder photosynthesis, thereby causing serious disruptions in the food chain. We hypothesized that analogous events occurred in Earth's past, albeit with even more drastic declines in primary productivity. Drabon did not participate in the study, however, he has written research concerning the potential events that transpired when a colossal space rock, estimated to be the size of 4 Mount Everest, impacted Earth over 3.2 billion years ago. The study yielded an unforeseen outcome, revealing atypical behavior among marine plankton. Contrary to the researchers' expectation that these minute organisms would diminish swiftly and take time to recuperate, it appears that the ocean plankton may have already rebounded within 6 months and could potentially rise to levels unprecedented even in these typical climate scenarios, according to Dye. We successfully monitored this surprising reaction in relation to the iron concentration present in the dust, stated Axel Timmerman, co-author of the study, who serves as the director of the ICCP and is a distinguished professor at Pusan National University. Iron serves as an essential nutrient for algae. However, regions like the Southern Ocean and the Eastern Tropical Pacific experience a scarcity of this material. If the iron levels in Bennu are substantial and dispersed throughout the ocean, it may lead to extraordinary algae blooms, particularly in diatoms, which are rich in silicates, potentially lasting for as long as 3 years as indicated by the study. Algal blooms would similarly draw in zooplankton, which are minor predators that consume diatoms. The projected surges in phytoplankton and zooplankton could prove beneficial for the biosphere and may assist in mitigating the rising food insecurity stemming from the prolonged decline in terrestrial productivity, stated Dye. Nevertheless, the predominance of diatom blooms may adversely impact ecosystem diversity. For instance, diatoms possess a competitive edge over smaller phytoplankton in iron-rich environments of the Southern Ocean. The significant proliferation of diatoms could inhibit growth of smaller phytoplankton. The favorable reactions exhibited by certain life forms, particularly simple, unicellular organisms, have been documented in the history of Earth, according to Drabon. The researchers intended to investigate the potential reactions of early humans to asteroid impacts by simulating their life cycles and food-seeking behaviors. Drabon emphasized the significance of understanding that impacts on Earth are unavoidable, with the only variables being the timing and magnitude. While the catastrophic event that led to the extinction of the dinosaurs is widely recognized, it is essential to note that smaller impacts are considerably more frequent, making the study of their consequences vital.